When activity's low, we will still gladly show you space weather. And from various views, we will always share with you the space weather. Talking about a featureless sun. Here's 171 angstroms. No sunspots, no active regions really. Seeing some weak, diffuse coronal hole wind streams coming through. And here's some anomalous data for you. There's your magnetic field lines at 1700 angstroms. And yeah, I guess the western disk of the sun, the western portion of the solar disk has no magnetic fields. Cheers. Seriously, this is some sort of anomaly. Not exactly sure how this happens. If anybody's aware, please explain it to us in the comments. Now, before we go on here, I'd like to give quick shout outs to our featured channels, officially endorsed channels, that is. If you're not subscribed to these, if you haven't watched their videos, please do so. Head to youtube.com/smashomash. Look on the right side, and there you've got Sky Scholar, Suspicious Observers, Adapt 2030, David Lapointe, Tony Heller, Thunderbolts Project, Starman, and the most recent addition, the Electric View. We want to feature something from one of Sky Scholar's videos, as we regularly do. A little talk by Sky Scholar host Dr. Pierre-Marie Robitaille from a 2014 talk at the Electric Universe, The Sun on Trial. What this is a explanation of his paper, 40 Proofs Debunking the Gaseous Sun. Let's watch some clips.
You have to drive energy processes onto the sun. So you get flares. Why? Because you have magnetic energy transfer onto the surface. So now I got energy flowing towards the sun. But in the solar winds, I have to have heat going away from the sun. Well, you can't have the heat going in both directions. It's either going towards the sun or it's going away from the sun.
So there we heard Dr. Robitaille talking about the acceleration of the solar wind and the way heat appears to be leaving the sun as opposed to coming from the sun. So that raises some of the issues regarding the solar wind. Let's see some more. Next, Robitaille will talk about the elements present in the corona.
So there's emissions. I just showed you a coronal emission, a coronal mass ejection in the movie. So the sun is sending stuff up into its atmosphere. The chromosphere possesses both free ions and atoms and sparse distributions of dense hydrogen. But that is not metallic hydrogen. It's molecular in nature. And it results from condensation reactions in this region. And the transition zone does not exist.
And now Robitaille goes on to talk about the differences in solar output during solar minimum versus solar max. At solar max, we get a lot of activity coming out of the equator of the sun via sunspots, and at solar minimum, we see persistent coronal holes at both poles, which is essentially the sun outgassing, the sun removing the gas plasma from the intercalate layers.
When it's quiet, so you look here at the top here, the top of the figure, 1996 and 2006, that's when the sun is quiet. So when the sun is quiet, there's hardly any helium-2 lines on the outside. It's quite silent. But when it goes active, it starts expelling helium. So why does the sun go active? Because it's degassing its non-hydrogen elements. It wants to kick everything out. So when the sun is quiet, at the poles, you have coronal holes. And in those coronal holes, material is leaving the sun at constant rates. And so now the sun is degassing. It's able to degas its poles when it's quiet. But it can't do anything about the equator. Any atoms that are non-hydrogen made in the equator interior of the sun, they're trapped. They can't get out. Why?
He's talking about atoms that are stuck in between the layers of the metallic hydrogen lattice structure.
Wait a minute. So because they can't get out, the sun has to go active to degas the equator. And so that's why we see the sun going active. So here's an example that we know from graphite again. Graphite can make intercalate compounds. Since I'm an inorganic chemist, I know this. Okay?
The way this works is, as you get farther into the sun, you get denser and denser lattice structures. In between those lattice structures, we have what's called an intercalate region. And when those get too massive, they have to find a way out so that the sun can reach equilibrium. It's trying to throw those non-hydrogen gases out. Anyway, watch the video. We'll leave links in the description. Let's look at some more normal stuff here, like the real-time solar wind. BTBZ's converging again. No major swings there. Phi angles at 342. We saw a couple very short-lived coronal hole magnetic connections there. This looks like one over here also. Solar wind density is right below 10, maybe 9 protons per cubic centimeter, and we've seen a recent slight downturn in the solar wind speed, which is now around 350 kilometers per second. Next, take a quick look at spaceweathernews.com to see that the X-ray flux is still pretty completely flatlined. We see the magnetometer is looking pretty steep there. It dropped to a very low level, and we're going to see that drop to an even lower level when the heliospheric current sheet crossing occurs. KP index is up to 2. Here's your cygnets forecast, which is still through the 16th. It looks like it hasn't been updated. I'm not exactly sure how often they update that. And since it's a model, I don't care that much anyway. Here's the electron flux, and you can see the characteristic drop-off with this coronal hole wind stream. This is probably going to pop back up to normal levels very shortly. Charging hazards are pretty minor here, if not non-existent, and the F2 ionosphere layer is looking a bit on the discharged side. There's your auroral forecasts. Moving on. All right, let's take a look at what the 10.7 centimeter radio flux is and has been. So, yesterday it was up to 70, so it's been 68 to 70 for the past week or so, as high as 72. And we'll leave links to this also. Now let's look at the Gong 2 as we predict the next crossing of the heliospheric current sheet here. This data is 1 hour and 21 minutes old. And you see this orange line going from the Earth to the corona. That line is going to eventually leap across. And actually it's going to come all the way down like this. Let me stop that so I can explain how that works. So, let me advance that a little more here. Jeez. Go to the last frame. So, you can see the Earth has got this magnetic connection here. As this approaches the edge of this rift here, eventually it's going to snap across like this. When it does it, we're going to get an extreme drop in the magnetometer and then a spike back up in the magnetometer. Now, whether it's a really strong spike depends on the density of these lines right in this area. And since those lines are looking dense, it's not going to be a real direct connection, so the magnetometer won't jump up too high, but it will drop down to 0, and there will be a fluctuation because you can get like a phasing where you're kind of connected to both sides of the current sheet at the same time. Hope that makes sense. Next, let's look at magnetosphere movies here. This is the density, plasma density that is. You're going to see this drop down a bit at the end, as we've seen the last 2 days. There you can see a little density drop, but the magnetosphere is maintaining its outward shell density. So this is a less significant density drop than the last 2 days. Let that play through again so you can see that play out. Here comes a low density, but the high density blue shield at the front remains in place. A good demonstration of what a minor density drop looks like. Now let's look at the pressure. We should see a drop off in the pressure at the same part of the video. And there's your pressure drop. And a return to a more nominal pressure. Now we have seen some geospace perturbations here, so we're definitely going to take a look at that. Not to mention some earthquake uptick. So you can see some geomagnetism there creeping down between Alaska and Hawaii. Also some pretty dense fields all throughout the Pacific Ocean, the Southern Indian Ocean. Looks like we got fields coming out of... I'm not sure where they're coming out of. We're going to look at this from the poles after we let that play through one more time. Some significant magnetic perturbations on the planet. Not at a super high level in nanotesla, but kind of all over the place. Here's a view from the poles that should show you the origin of those fields. Looks like the spillover is mainly coming out of the North Pole. Moving on. Volcanoes today. We've got Karimsky, there we go. Emitting an ash cloud to 8,000 feet of altitude. Shivaluch, 16,000 foot ash plume. Bezimiani. Anybody knows how to pronounce these things, let me know. I think I got that one. 18,000 foot ash plume. Popocatépetl. Volcanic ash cloud has dissipated in satellite image. Revenador, 16,000 foot ash plume. Sabancaya, sporadic puff emissions. And Nevados de Chilean, no volcanic ash emission, yet for some reason on the list. Also, Stromboli is almost constantly spewing lava into the air. Next, let's take a look at this earthquake uptick. And let's start out with someplace quite close to home. As our regular viewers know, we're located in eastern Pennsylvania. And check it out. A 4.7, 219 kilometers off the coast of Ocean City, Maryland. Looks like it wasn't felt on the land based on the map, but that's not one you see every day, is it? Now, let's go back to the largest quake we've had in weeks. There was a 6.6 last night in Vanuatu. Also, we got a 5.7 in the Philippines, 4.0 in California, 5.2 in Peru, 4.7 in Indonesia, 4.9 in Indonesia, rather, 4.7 off in Maryland, which is nowhere near a plate boundary, by the way. Dominican Republic, 4.5, 4.6 Indonesia, 5.1 in New Caledonia, 4.0 in Caldwell, Kansas. Jeez. So yeah, it looks like an uptick to me. We got earthquakes going on in the middle of the craton. Moving on. Check it out, universetoday.com, an article exposing the utter failures of astrophysics. Turns out that a new technique to figure out how old stars are is going to utterly fail at figuring out how old stars are. Why? Because of the gaseous plasma model of the sun. They're trying to get their margin of error from 10 to 20% all the way down to 3 to 5%. And guess what? It ain't gonna work. What time is it? Not gonna work a clock. So, here's your main sequence chart. Very common chart. It can't explain these things. It can't explain these things. It thinks it's explaining these things. And it's wrong. Completely wrong. The measurements of the mass based on brightness and the age based on brightness and all this stuff, I mean, it doesn't work. Metallicity is also another technique used to measure the age of a star. Metallicity is referring to chemical elements besides hydrogen and helium. In astronomy, everything more massive than hydrogen and helium, everything, lower on the chart beyond those two elements are considered metals. And when you measure the metallicity of a sun, all you're measuring is what's going on at the surface. It tells you nothing about the internal workings of the sun. So in any case, they've got stars in the Milky Way galaxy that are dated to be older than the galaxy itself, which, while that may not be an impossibility, totally falls outside their gravitational accretion theories. We'll leave links to the article. Have a read if you like, but I don't think this represents any kind of an advance in dating stars. Speaking of dating stars, our next article is about Kim Kardashian and Kanye West. Just kidding. Check this one out. China has sprouted plants on the moon. Yes, that's right. That is a cotton plant sprouting right there. How awesome is that? They brought a whole biosystem, series of different plants, even yeast and fruit fly eggs, in a hope to create a little ecosystem there in its own module, complete with heat, radiation shielding, oxygen, water, etc. Another interesting article. Have yourself a read. Next, we've got a phys.org article. Somebody's doing laboratory plasma experiments, creating very, very realistic artificial solar flares in the laboratory. Quite awesome. Some of the phenomenon even does show up in visible light. Thank you, National Center for Atmospheric Research. Yes, well done. Next, we've got an alien landing pad forming in Maine. Some kind of spinning ice disk. Looks like in a river. Here's another view of this thing from the air. Just created by river currents, and I'm sure it probably started to form in this area over here, and it got hung up in the backwater, and there you go. That is just awesome. I wonder if you could ice skate in place on this thing. Quite odd. I like it. Don't go out on ice skate on it, folks. It's pretty freaking dangerous. Next, we got an article on ScienceAlert.com. Alert, alert. Astronomers have found evidence of a big black hole wandering our galaxy. Now, this is the kind of phenomenon I was aware of in the mid-90s already. Somebody thought they had tracked a neutron star, some kind of a massive object, traveling across the galaxy faster than all the stars, causing massive perturbations and some lensing effects. So it's a known thing that some of these massive radio sources, massive plasmoids, whatever you want to call them, are moving around in a contrary fashion to the rest of the stellar motions in the galaxy. So here's an article about that. All right, it's getting late. We got to get the video up. So here's a view at 94 angstroms. Remember, when you're doing real cosmology, don't drink. And if you drink, do real cosmology anyway. We need it.